This example will look at comparing two samples to each other instead of a sample to a specific number. Example 5. A researcher wishes to see if there is a difference in the cholesterol levels of two groups. A random sample of 30 is tested and has a mean of 223 with a standard deviation of 5. A second sample of 35 has a mean of 229 with a standard deviation of 6. Assume normal distribution for both populations. At alpha equals 0.05, is there a difference? All right, now similar to what we've seen in Chapter 8, the null hypothesis and alternative, in this case, instead of mu equal a number and mu does not equal a number, we're going to have multiple mu's. We have mu1 equals mu2 in the null. Mu1 does not equal mu2 in the alternative. So it's parallel in the fact that you still have the equals in the null, not equals in the alternative. Now, the rules in terms of picking which test get much more difficult when you are comparing two different samples. When you have small samples involved, the statistics gets much more difficult, and there's a lot of discussion. The book has changed its mind a couple times over the revisions over the years, and you'll see statisticians argue about this, and it's really a discussion that takes place beyond an intro course, in my opinion. So what we're going to concentrate on here, I showed an example using two large samples to avoid that problem. So there are techniques to deal with small samples, but they're advanced techniques, and no matter what you do, there are criticisms that can be levied at it. It's a difficult problem. So we're going to concentrate here on the two large sample size. Since it is two large samples, we would use the Z version of the test. When we have a two-tailed test, equals versus not equal, our critical value are positive and negative 1.960. We've seen that in past videos. You know, you can either go to the Z table and figure out 95%, or you can go to the T table, go down to the Z infinity row for two-tailed and alpha equal 0.05 and find 1.960. Now, the formula for the test statistic, it looks worse. It's not as much worse as you initially think. The first piece in the numerator, you take x sub 1 over bar minus x sub 2 over bar. So we're comparing the sample means. Minus mu sub 1 minus mu sub 2. So those are the population means. Now, the interesting thing here is we're assuming that these two are correct in our null hypothesis. So this second piece of the numerator, the second factor, drives to 0. So it goes away. So the first piece of the numerator, we go and find we had 223 and 229 for our means, and we substitute in for them. And over all this, our numerator value is going to go to negative 6. So this second piece, this mu1 minus mu2, always drives to 0. It basically falls out of the equation for us. Now the denominator is a little bit of a mess. We have square root of sigma 1 squared over n sub 1 plus sigma 2 squared over n sub 2. Now, we don't know the population standard deviations, but we have large samples. We know the sample standard deviations. We substitute those in. The important thing here is you need to match up your standard deviation in your sample. Okay, you could flip-flop the order here of what's 1 and what's 2, and it wouldn't be a big deal, but you do need to keep matched up the fact that the standard deviation here of 5 goes with a sample of 30, and the standard deviation of 6 goes with a sample of 35. If you would cross those, you won't get the proper answer. So we have 5 squared over 30 plus 6 squared over 35. I stayed in fractions here, 25 over 30 plus 36 over 35. At that point, it gets ugly, so I went to the decimal. 25 over 30 plus 36 35ths is 1.862. Square root of that, 1.365. Negative 6 divided by that gives us a test statistic of z equals negative 4.397. Our critical value is negative 1.960, also positive 1.960. So again, as with a lot of the examples we've looked at, we reject the null hypothesis. There is a difference between the means. And to look for the p-value, I wanted to find the value for that test statistic of negative 4.397. So I used dot equals norm dot s dot dist, negative 4.397, true, It gives me a number again in scientific notation. Because this is a two-sided test, plus or minus critical values, equal versus not equal, I need to double that number. Even with doubling, when I move the decimal point, I end up with 0.000011. If you're rounding to just a single decimal, as the book would typically tell you to do, you'd be left with just 0.00001.